students, and welcome to this lecture number 2 of dynamics of machinery. So today we will be carrying our lecture on from the previous portion where we left, which was studying about useful and harmful vibrations. So we saw some examples of vibrations, like where it is useful, where it is harmful. It is useful for ultrasonic cleaning and other purposes, while it is harmful in cases of centrifugal compressors where it creates fatigue. Right? Today we will be discussing about very important topic, that is periodic and simple harmonic motion. Periodic and simple harmonic motion. So where does the word periodic motion come from, or why we are studying it in dynamics of machinery? In the previous lecture we have seen that what is vibration ultimately? It is oscillations or oscillatory motion. Let's say oscillatory motion. Let me write it down in a better way. Oscillatory motion which gets repeated after certain time interval. So it could be something like a motion which repeats itself after certain interval of time. Like say this cycle is there for a time t, and it is again getting repeated after again time t1. It is getting repeated again, it will be getting repeated like this, right? So it can be one which repeats after certain time interval. This thing which repeats after certain time interval, we call it as periodic motion. Periodic is the one which gets repeated after certain time interval. So what is the other one? The other one is nothing but, say for example, I have a wave which moves like this. Now you can see there is one wave for time interval t, and the other wave has taken more time. Here this wave has taken very long time, right? So it is a very big time. Say for example, I am talking about t dash. It is very big as compared to t. So you can see that the oscillations are there, but they are not repeating themselves. Amplitude is also changing. What is amplitude? We will be discussing it in the next lecture. That is the terminologies of any vibratory system. But right now just think that what is amplitude? It is the maximum height reached from the mean position. So this is amplitude. I will take it or cover it in a very brief manner in the next lecture, so not to worry about it right now. So here you can see that within time, here it is t, here it is t dash, the time intervals are different, and I'm not at a particular point. Say for example, I talk about this point, I'm not able to know anything, or I'm not able to predict my behavior of oscillations. That is, my behavior of oscillations is unpredictable, you can say. Unpredictable. So what kind of vibrations are this? These are known as random vibrations. Where you cannot predict is something which is known as random. So these are random vibrations, right? So we would not be more concerned with random vibrations because they are not right now for our like they are not in the scope of the syllabus right now. We will be discussing majorly about periodic Let me again write it down. Periodic vibrations. So what are periodic vibrations? Like when the oscillatory motion repeats itself. You see, it was repeating itself within, or let me better say after, repeats itself after certain time interval, comma, it is called periodic motion. So let me draw it in a figure. Say for example, this is the displacement and this is time. This is time and this is displacement x. The wave moves like this, here, here, again goes like this, this and carries on. So you can see that the movement from this point to this point takes in an interval t1, and from this point to again the same point takes in an interval t2, and here t1 is equals to t2. Right? So the motion gets repeated after a certain interval of time. Okay. So whenever motion gets repeated after a certain interval of time, we call it a periodic motion. One major other thing that we need to discuss is simple harmonic motion. Now, simple harmonic motion is nothing but a special case of periodic motion. Why I am telling a special case of periodic motion? Because in simple harmonic motion also, the very first condition of periodic motion, that is you can say the repetition of oscillations after a certain interval of time, is there. But there is something which is additionally present in simple harmonic motion, which we will be discussing in this lecture, and understanding that how a simple harmonic motion gets differentiated from periodic motion. So let me take an example of a simple harmonic motion. When I say a simple harmonic motion, you can consider the best example as, say for example, you have a string and you have a bob and you have connected the string, and now you are rotating this with the help of with an angular speed omega. So this bob will cover a circular path. Say for example, your angular speed is omega and it is uniform. So this object will move on a circular path. Right? So let us say that the extreme radius is capital X. Right? So if I want to mark the instantaneous position, of the object, say for example at a time t, so let's say that at time t the object is here. It has started its journey from this point, say for example A, and it has reached to a point B. So what I'm doing is, it has covered a distance theta. Right? You can see that this is an angle theta which it has made. We all know that theta is equals to omega t, right? Where t is the time period after which we are marking its position. So let us say the center is O, this point is P. So you can see that OP will be equals to, this is the radius, this is X. You have one component of the radius, horizontal component, and one vertical component. So OP would be equals to, it is theta is here it is 90, so 90 and theta forms the base. So we have X cos theta, and VP or PB will be equals to X sin theta. We will discuss of any one thing, and then probably will conclude this in the other way, so you will get a better idea. Right now, let us take the vertical position from the mean axis, right? Mean axis. Now why I'm selling this as the axis? Say for example I talk about the point B at any instant, and let me draw it again. Say for example this is the circle, you have your center axis. The point B was originally here. Now it has moved to certain distance here. When I instantaneously mark its position on this line x dash, it would have reached at this point. Say for example after a certain interval of time, it would have reached this point. Then it would have come to the center. Again it would have moved to a point like this. Then it would have moved to a point like this, ultimately here. So the point started from B, continued to move in this direction and went to A. Now again if you continue this rotation, then the point will be moving back to this side and ultimately it will travel back to the point B. So if I consider points B, O, A, then my mass had started to move from B, moved towards A in this direction. Again, after the half rotation, it started coming back and it has started to oscillate about this point. Oh, it is constantly moving from B to A, again coming back from A to B. If I consider thus this center line. So which kind of motion is it doing? It is doing a periodic motion. Because what was the definition of periodic motion? It is like oscillations which repeat after a certain interval of time. What is happening here? The object is continuously moving with some angular velocity omega. So after a certain time it will obviously cross this, and it is moving with a uniform speed. So it will continuously be moving from this point B to the point A, again to the point B. Is it okay? So let us take this displacement at any instant. So when I take the displacement, let me draw the figure again. So I have this, the initial position was here at A, now it has moved to point B. I'm dropping it or drawing a perpendicular P. This is an angle theta, this is point O. So the displacement, let us say displacement at any instantaneous time, instantaneous displacement is, let small x, so it will be equals to capital X sine theta, but we know that theta is equals to omega t, so I can write it down as x equals to x sine omega t. Now what is velocity? It is equals to dx by dt, that is rate of change of displacement. So when I differentiate capital X sine omega t with respect to time, I get this x is constant, so it will come outside of the derivative, and I will differentiate d by dt of sine omega t. So using the chain rule, it comes like x omega cos omega t. Again, if I want acceleration, then what is acceleration? A is equals to dv by dt. So I need to differentiate x omega cos omega t, which was my velocity. So this would give me x omega is common, and I would be differentiating only cos omega t. What is differentiation of cos? It is minus sine omega t and one more omega. So ultimately I am left with x omega square sine omega t. Let me write it down on another page. Sorry. So acceleration would be coming like minus x omega square sine omega t. Velocity was x omega cos omega t, and displacement was x sine omega t. Now if you know that velocity, I can represent it with x dot. X dot means it is dx by dt, that is derivative of x with respect to time. I can represent it with a dot on the x. So what is acceleration? It is dv by dt, which is equals to d by dt of velocity. What is velocity? It is again dx by dt. So it is d square by dt square x. So how can I represent this thing with the dot notation? I will write it down x with two dots. So if you see this equation, I can write it down as x double dot is equals to minus x omega square sine omega t. But you see, what is x sine omega t? It is small x. So I can replace x sine omega t here with small x, and ultimately I will get the equation, that is x omega square x equals to 0. Here, this equation is known as the fundamental equation of simple harmonic motion. So let us discuss it in a little bit detail. The equation was x double dot plus omega square x equals to 0. Here, if you can see, I'm again writing it and I'm taking the term to the right hand side. So it will be x double dot equals to minus omega square x. And I can write it down that x acceleration is directly proportional to the displacement x. So simple harmonic motion, we started with something like it is a special case of periodic motion. So if it is a special case of periodic motion, it will obviously be following all the rules of periodic motion, that is repeating itself after certain time interval, right? But from this equation here, I see that a periodic motion is called simple harmonic only when its acceleration is proportional to the displacement and always directed towards the center. So if in a periodic motion the acceleration is proportional to the displacement and it is always directed towards the center, we call it that the periodic motion is an simple harmonic motion. Otherwise, you cannot say that a periodic motion is a simple harmonic motion. So, let us take some examples. Periodic motion and SHM. You can see that the moment of planets around the sun, an example of periodic motion. Here you can see a simple pendulum, the best example of SHM. Always the acceleration is proportional to the mean position or directed towards the mean position. Say for example, you have a bob, you displace it to some other place and leave it from here. The acceleration will always be directed towards the mean position. What is this? This is the mean, or you also call it equilibrium position, right? So every periodic motion is not simple harmonic motion. Simple harmonic motion has two major components to deal with. One is that the motion must be periodic, that is the oscillations must repeat itself after a certain interval of time. And the secondary thing is the acceleration must always be directed towards the center point or the mean position or the equilibrium position. So I hope that you all are cleared with the difference, like where the periodic motion gets separated from simple harmonic motion. Ultimately, simple harmonic motion is a sub classification of periodic motion, you can say, because it falls under periodic. Like periodic, you can say that periodic motion is something which repeats itself after a certain interval of time, and simple harmonic motion is also a special case of periodic motion, but here the acceleration is always directed towards the equilibrium position. So with this slide I want to conclude that when I say a periodic motion, it is a motion which repeats itself after an equal interval of time. And what is SHM? It is a special case of periodic motion. So it will also be a motion which will repeat itself after a certain interval of time, but its acceleration is always directed towards the mean position and is proportional to its distance from the mean position, which we saw with the help of an equation, that is x double dot is proportional to x in case of an object moving around a circle holded from the center, right? So the motion of a projection of a particle moving around a circle with uniform angular velocity on the diameter is the example of a simple harmonic motion, which we have already seen. Suppose I have an object and it is moving in a circular fashion. At any instant, suppose I project its motion onto the diameter. This is the diameter, right? So it will obviously perform a simple harmonic motion, will move from here to here for this half rotation and will move the other side for the other half rotation. So this is all for today. Our discussion ends here. We will be starting on with the definitions of we will be discussing definitions like frequency, what is amplitude, what is time period in the next lecture, and also we will be discussing about the basic classification of vibration from various aspects. So I will be uploading lecture 3 also very soon. So up till then, please do like our video, subscribe our channel, and also follow our updates. Also you can ask your questions if you have any through the comment section given below. We would be trying to answer your questions as soon as possible. Thank you very much.